So yep, in this video we said we are going to look at PCA, the coding part of principal component analysis in Python. So yeah, we get our principal component analysis from sklearn, and that's just it. We put our parameters here. So in this case we are going to use 784, and that's for a very particular reason that I'll explain as we go. Usually you need to put the first step is usually to just put all the features. Originally, in our original data set, we had 784 features. It's good practice to just start off your PCA with the same number of features, and you will see why. So we're just going to use the same number for your principal components will be the same number of features that you have. You'll see why. And then here we instantiate our PCA with the number of components and all of other variables that we have here. Then we fit it. We are fitting it on our X-train. So here it's now applying principal component analysis to our X-train, and then we just create a data frame, X-train PCA coming from the PCA, and we make it a data frame. Actually, we make it a data frame on this line. So what we are going to now look at is what we want. We want PCA to capture the salient information from the original data set, right? And it's doing that. It's doing that here. This is where it starts generating principal components, right? Once they are generated, those components, then we'll look at how many components we really need to capture the information that we need. The information to capture as much information as possible. What am I saying? You remember here I said 784. It's good practice to just start with 784. It's because we do not know how many principal components are going to capture enough information. So we can put 20, but maybe 20 is not going to capture enough. We can put 100, but we are not quite sure. So it's always safe to start with everything 784, because we know that in 784 all the information is there. And then we'll make a decision. We'll make the decision just now. So yeah, with this code here, we are saying percentage of variance captured by all 784 the new 784 principal components, right? Here we just print them. You use this function PCA. You can just call the explained variance ratio. So it's saying variance explained by all 784 principal components is 0.9999. This is actually 1 or 100%, right? So the all 700, it is expected. We expect all 700 to explain every variance that is in the dataset, the original dataset, which makes sense. Even though the 700 are now principal components, are not features, are not the original features we had, but having all 700, we've captured every information that was in the original dataset. Perfect. Now at this stage, we want to evaluate PCA and choose the right level of number of components, right? Because here, as you can see, we have not reduced the dimension. We've just moved from 784 in the original data set with the number of features to 784 components, principal components. We haven't reduced the dimension, but PCA is supposed to be dimension reduction technique. So this is now what we are going to do. We now start evaluating PCA, and the way we evaluate PCA is to look at the information that is captured by a certain number of principles. So 784, they capture 100% of the variation. But what we can do now is let's look at the number. Let's look at what we're going to do here is we're going to say important. We're going to create a data frame, with all the with the importances, with the variances, right? And when we do that, we can go through the code. This is just transpose if you don't know. We're going to say variance captured by the first 10 components. So we are going to say for the importance, we just get the first 10 components, and we sum them up. We sum all the variances, and this is the result here. Variance captured by the first 10 components, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 summed up is 48%. Okay, so if we take only the first 10 components, we are going to retain only 48% of the information that was there in the original dataset. Cool. What if we take the first 20? the first 20 are going to explain 64%. And when we say first, principal component starts with the ones that capture the highest variance or the highest information. So these ones are the first 10, they are first by order of how much they have captured. So the number one variance is the one that, the number one principal component is the one that actually captured the most variation or the most information in the original data set. So when you say the first 10, those are the top 10. The top 10. So here we can say the top 20, the top 50 principal components is going to be how much variation? 82%. We are now capturing 82% of the information. We're going and going and going. We can go to 100, which is 91. 200 captures 96, and 300 principal components, they capture 98. They capture 98%. So as you can see here, if you take 300 300 principal components and not take 784, you're actually capturing 98% of the information that was there in the original data set. It's up to you to decide whether that's a high enough number to retention for of the information, or it's still too low. You can put 400, 500, but I think 300 makes sense. To make this more visual, you can plot a graph of the components themselves. You can plot a graph of the information being captured by the components themselves. So you see 0 was capturing close to 0. So 0 was capturing 0.9, 0.09, maybe 0.09, and then 1 was captured maybe close to 0.07 and stuff. So these are the principal components: 1, 2, 3, 4, 5, going like that. So the 10, when you add up the 10, when you add up what they're capturing, the first 10 components, you get to 0.48. So this first 10 they've captured 0.48. Yeah, if you want, you can put 0784. It's just going to be difficult to read. But this is the information captured by the first principal component, second principal component, third, fourth, fifth, and stuff like that. So you can actually plot them and see. But here we're just printing to say, if we put 350 components, how much information would you have captured? Probably close to 98.9 or maybe 99 actually. So there's no need for us to retain the 784 components. We can actually say, okay, let's just take the first 300 components. So that's what the graph there is showing. So this now, when we choose the 300, it has allowed us to reduce the dimensionality of the original dataset quite significantly, by half actually, by more than half, because while retaining a large chunk of the information that was there. We are now left with 300 with 98 or 99% of the information that was there in the data set, which is good. And it's not just information, it is the top information, the top variation, so which is very, very brilliant. That's actually all the information that we need, right? If we are going to pump the results of these 300 into another machine learning model, it's going to be much easier for it to separate the data points in that space. So there we can do anomaly detection, or we can do anomaly detection or pump it to another machine learning model. But let's just say we wanted to end here. If we wanted to end here, let's look at this one here. There's a function here, a scatter plot. So we want to prove that PCA is very, very efficient in capturing the information that is there in the dataset. Here it doesn't even know the labels. It doesn't know the labels. It just captures the information or the underlying structure of the information. That's all it does. As you remember, we never used any white train here. So it just captured the information, and it said, if you use 300 principal components, I've sort of understood the data set. And that's why you can use anomaly detection here immediately. You can use anomaly detection immediately because it has captured the cracks of the information in there. But let's just prove that it has actually captured the cracks of the information. Let's say we plot our observations in our original data set. If we plot them if we plot them, so yeah, this is just a diagram. It's just a diagram that we are going to. It's a diagram that we are going to plot the results of our PCA. We're plotting the results of our PCA in 2 dimensions. Specifically, what we are doing here is we are displaying a scatter plot of the first and second principal components. So the information that has been captured with the first and the second. So one of them, this is the first vector and this is the second vector. For it because we can only plot really in 2 dimensions. We can do 3D, but it's going to be difficult. But if we plot the information in the first and the second dimensions, because it's a table, it's a data frame, right? It is a data frame, and because it's a data frame, we can plot the 0 and the 1, columns like that, and plot the information. And we are going to color here. It's going to be important. What we're going to do. So yeah, this is just that you can go through the code itself, but we're going to color this code by the Y train. We're going to color the code by the Y train, the actual label of the original image. So if the image was a 5 and the information that we've captured here is a 5, we're going to color all 5s the same. Here, these first 2 are going to group. They're going to sort of like be plotted in the same region. But to prove that they're actually plotting in the same region, they've captured underlying information of 5s in the same region, underlying information of 6s in the same region, underlying information of 9s in the same region. We're going to plot it. Right? When we plot them, we are going to color them by the number. And as you can see, all the blue are actually by themselves. All the red are here. All the green are here. All the orange are here. Which sort of makes which means principal component analysis looked at the underlying structure. What makes a 5? And it captured all that variation. And then when we plot the information from just the first and the second vector, it seems like it's grouping them. This could be the zeros, I think, with the labels. This could be the zeros. It grouped the zeros by themselves. It didn't even know that it's a 0. It doesn't even know that. It just grouped by the information that it was capturing. You see, the zeros are now by themselves. The 1s are by themselves. The 2s are by themselves. The 3s by themselves. If we could plot in multi-dimensions, you could actually see that it has done a very good job of separating. Especially if we can plot the first 300 that we got here, the 300 that captured 98% of the information. If we could plot in 300 dimensions, you'd see that we have actually separated them. Principal component analysis has actually separated these numbers, which is mind-blowing. It's actually mind-blowing. And if you want, yeah, you can just do another plot. Like, let's say if you plot it using the most important factors, yeah, you can look at this. But I just wanted to emphasize this part here. This is one I really wanted to emphasize, that principal component analysis really did not know what the label is. We never used the label, but it captured information. And if we plot the first 2 principal components, first component on the x-axis, second vector on the second component on the y-axis, for example, and we plot the information that those two have, right? What we are going to see is this, as you can see, which is insane, especially when we color it by the actual label. These 9s, these look like 9s, I think. The 9s are by themselves here. These look like 8s. This brownish one here look like 8s. The dark brown look like 5s. The 5s are now are right here by themselves. In PCA, like I'm emphasizing, PCA did not even know this structure. It just captured the salient information. Now imagine if you could plot in 300 components. It was going to be so wonderful, because we would have shown the separation. The information it would have captured would have been 98% of the information captured. It was probably going to be even more cleaner. So that's PCA. A very, 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 very important part, that it understood the underlying, just how powerful PCA is in learning the underlying structure of the dataset without any labels whatsoever. There are no labels here. even in just 2 dimensions, it's showing proof that it has learned information. In 2 dimensions, it has learned good enough information to actually separate them to some extent. If you want, here you can say, you can remove this and say the first 2 components, and here you just say you change this to 1 and run it, and you see how much information led to this. Or here you can just add 0.009 plus 0.007, so it's probably going to be 0.16. Only 16% of the information is giving us this. Now imagine if we get 98% of the information. It's going to be incredible. It's going to be incredible. That's the power of PCA. So in the next video, we are going to move on to incremental PCA. We've understood the basics of PCA. In the next videos, it's just going to be like we'll be looking at it in Python and just discussing a few changes here and there. But otherwise, this is the structure of how we are going to discuss all types of PCAs. So stay tuned for that video where we do incremental principal component analysis.